When we learn arithmetic, we treat numbers as distinct, stable locations on a number line. A number is a fixed point with an exact value. But try to add two irrational numbers together, like pi and the square root of 2, and that stability collapses. Basic addition requires us to align columns from right to left. We start at the end of the decimal sequence, add the digits, and carry the 1. Because irrational numbers possess decimals that never end and never repeat, there is no rightmost column. The addition is functionally impossible to begin. Modern calculators hide this mathematical paradox. By instantly truncating the infinite string at 10 or 15 decimal places, the machine provides a clean, finite approximation that allows us to ignore the underlying problem. If fundamental operations like addition fail when applied to non-periodic infinite decimals, it means our digit-by-digit view of mathematics is broken. To calculate with the infinite, we have to rethink exactly what a number is. In his definitive pre-calculus text, Russian mathematician A.P. Kiselev confronts this issue directly. He refuses to gloss over the infinite nature of irrational quantities. Kiselev discards the attempt to define an irrational number by its exact digits. Writing out a never-ending sequence gets us nowhere. Instead, he defines a real number by what it is trapped between. An irrational number is treated as a shrinking gap bounded by rational approximations. Defining a number by the boundaries that contain it, rather than searching for an unresolvable exact value, provides a logical workaround to the endless decimal. This transition makes operations on irrational numbers computationally possible. This diagram shows the geometric origin of the irrational number, the physical process of measurement. We have a line segment AB and a shorter measuring unit, CD. We start by finding how many whole units of CD fit into AB. Here, it fits 3 times, but it leaves a smaller remainder segment, which we label EB. To measure that leftover remainder, we logically subdivide our measuring unit into smaller fractions, like tenths, and see how many microsegments fit into EB. For standard rational segments, continuing this fractional subdivision eventually aligns perfectly with the end of the line. However, for incommensurable segments, no fractional subdivision will ever perfectly align. This eternal physical mismatch generates the infinite non-repeating decimal. Rational numbers serve as the measure for commensurable quantities. Irrational numbers exclusively measure these incommensurable quantities. No matter how incredibly small, tenths, hundredths, thousandths, a physical remainder always persists. An infinite decimal is the numerical shadow of a physical measurement that can never be completed. Translating this geometric concept to algebraic roots requires a systematic approach. If we want to manually compute the exact value of an incommensurable number, like the cube root of 2, we have to build a boundary trap. A number line spans 1 to 2. A target sits at the unknown cube root of 2. Kiselev uses sequential testing. First, the integer test. 1 cube is too small. 2 cubed is too large. The exact root lives in this space. The lower bound is the deficiency, and the upper bound is the excess. Stepping through the tenths, cubing 1.2 is less than 2, and 1.3 overshoots it. The gap shrinks. Testing hundredths increases precision. 1.25 cubed is a deficiency. 1.26 is an excess. We do not calculate the true irrational number directly. We prove it exists uniquely by trapping it in a mathematical window that shrinks infinitely. This returns us to the impossible addition problem. We need a way to systematically add 2 irrational numbers. Let's call them alpha and beta. This table illustrates Kiselev's additive boundary framework, which bypasses the infinite decimal problem. We start with the known bounds of alpha and beta. Rule 1. Add the deficiency bounds. 1.7 plus 1.4 gives 3.1. This establishes a mathematical floor. Rule 2. Add the excess bounds. 1.8 plus 1.5 equals 3.3. This establishes our mathematical ceiling. As we increase precision to the hundredths place, the floor rises, the ceiling drops, and the space between them tightens. Extending precision to thousands squeezes the gap further until it is paper thin. Kiselev proves the true sum, gamma, is the unique value strictly greater than all deficiency sums and less than all excess sums. Using finite rational bounds means there is no rightmost column of an infinite sequence to worry about. We never have to carry the 1. This logic scales predictably. The exact same boundary rules govern multiplication, squaring polynomials, and extracting higher degree roots. Attempting to calculate the infinite with distinct digits is a dead end, but using converging logical bounds makes arithmetic on infinite sequences flawlessly precise. Defining numbers as boundaries dictates how algebraic properties and equation manipulations must work. Because real numbers are constrained by absolute boundary rules, operations performed on them yield highly predictable structural properties. We see this predictability in the fundamental property of radicals, shown here. The rule states that multiplying the index of a radical and the exponent of its radicand by the exact same number leaves the core mathematical value unchanged. Complex algebraic formulas are entirely derived from this logic. They are inevitable consequences of how real number boundaries scale. We start with physical measurements that can never be completed and use converging limits to resolve them into absolute algebraic certainty. Classical texts like Kiselev's algebra demand that students confront the infinite directly, rather than obscuring it behind digital approximations. True mathematical capability comes from understanding the logical limits that constrain numbers, not just memorizing the output of a calculator. Thinking in terms of shrinking intervals directly prepares the student for the formal definitions of limits found in university analysis. Kiselev's construction ensures that the infinite remains grounded in logic. It replaces the endless search for an exact decimal with a sequence of finite, repeated